Okay, welcome everybody, welcome back. I know things are kind of crazy right now with coronavirus, but we're just gonna do it this way from now on. So, how we doing? Yeah? You okay? You okay? Yeah, okay. Um, here's what I'm thinking, what we're gonna do with this video series. We're gonna change up some of the topics just a little bit. We're going to focus on these old equations, the ones that we've been looking at all semester. D, D, T, H. There we go. So we're going to focus really on these as we go through the videos. I want to get into equations of motion. In the next couple of weeks, we're going to have an exam on each of these three parts individually. So we know that if we take these equations, we can break them up into chunks, right? We can say that here on the left, this is effort, forces and moments. Clearly, we're taking DDT of this stuff. We know that we know what these are going to become. These are going to be I omega dot plus omega cross I omega, and here we've got mv dot. So we need to be able to define all the different parts of this stuff. So if here is effort, then we've got some terms associated with mass and inertia. And then we've also got terms associated with acceleration. This would be your kinematics. So before spring break and before everything went belly up, we did acceleration and we did mass inertia. So neither of these we've done exams on them, right? The original plan was to do exam 2, cover acceleration and mass and inertia. What we're going to do is we're going to spend about 2 weeks. We're going to spend about a week on videos for effort, on forces and moments. And then I'm thinking we do about a week and a half of just problems. I'm going to come in, I'm going to do 2 or 3, 4 problems a week, and I'm going to put those up next week. And then we're just going to practice these 3 parts. We're going to practice all 3 of these parts, and we're going to have an exam not on putting them together, but just on very clearly and thoroughly defining all 3 of those parts. So that's what we're going to do in the next 2 weeks. I'm going to figure out the best way to do exams, and we're just going to move forward. So there's a couple other topics along the way. In a normal semester, I would do things like conservation laws. We're going to take conservation laws, we're going to take impulse momentum, we're going to take all of those kind of special topics. We're just going to move them to the end of the semester. Okay, I think everybody's going to be fine with that. If you have a concern about doing it or something, let me know. I know that some of those are still going to be on the homework, so we will talk about them. I'm just not going to put them on exams until the end. Okay. So today we have to do some videos. Let's do some videos on forces and moments and doing free body diagrams. We've got we're going to start off slow. We've got 2 examples. I've got a sliding block and I've got a pendulum. So let's do those real quick. Let's start with the first problem. First example we're going to do is just a sliding block. We've done this one several times. We know what the markup is. Here is our sliding block. We give this thing a name. We can call it A. We can say it's moving with respect to some inertial point, right? We can put a frame on this thing. There we go, frame A. And that is moving in it's moving with respect to some non-moving inertial frame in. So we know the drill with the sliding block, right? We've done this several times. We know that there's some displacement here, Q. We know that this thing is not going to rotate. So here's a problem. We would like to eventually apply Newton's second law and Euler's second law, ddt of h. Okay, so the standard write-up still applies. You go through all the things you've normally done. You define your rotations, define your positions, take derivatives, etc., etc. Okay, So we know how to do this. Next thing we want to do, if we're going to solve these equations, is we need to be able to build these expressions on the left, right? You've probably done free body diagrams in other classes. We're going to do it again and again and again. And if you're mechanical, you're going to take the K&D class. If you're aerospace, you take your aerospace classes. You come back for your modeling classes. You're going to do this over and over and over again in all your classes until you graduate. So just heads up. So this is what we need to write. We need to write that for this body. If you have 7 bodies in your problem, you need to do sum of forces and sum of moments for the 7 bodies, okay? For all 7 bodies. So body A, body B, body C, body D, etc., etc. You write sum of forces and moments for each one of the bodies. Now, in this problem, does it matter? Let's see. Where's my red? Where's my red? You took my red? Let's get started with writing these for this real simple problem. What is step 1? I would say step 1 is take a look at the problem and make sure you understand it, right? We're all comfortable with what this thing's doing. The true step 1, once you move on from that part, is we need to do a free body diagram. So, real simple question. Is this a free body diagram? Take a second. No. The answer is no, this is not a free body diagram. This is just the diagram of your problem. Main difference between this and a free body diagram. Well, free body diagram is going to be an exploded view, right? So it's all the parts, all the pieces, all the bodies separated from each other, and you don't see their connections anymore. So in this problem, clearly there's only the one body, right? Yeah. So we need to draw this body disconnected from all of its joints. Well, it has a joint here with the ground, right? So the free body diagram for this is it's just a block. That's it. So here is your free body diagram of A. And now we need to go through and we need to put some forces on it. So what are some forces in this problem? No? No opinions? Okay. Let's start with the easy stuff. This thing has gravity acting on it. So we're going to say mass. In this case, it's body A, so that should be, mass of A. M times G. What else? Well, right now, the way I've drawn it, it's just a body. In the actual problem, the body is on a slope, or it's on this surface, right? And what keeps the body from just floating off into space? Well, gravity. What keeps the body from going down? Well, it's literally on a surface, right? So how does that affect the body? Well, there is a distribution of force all along the bottom. Okay, it's a pressure. There's a pressure on the bottom surface of this from its contact with the floor. That pressure is going to keep the block from translating down. What we usually do, though, is we're not so concerned. Mostly we're not concerned about the distribution of pressure on bottom. What we'll do is we'll take that distribution of pressure, we'll simplify it, and we can represent it with a normal force in. We take all of that distribution of pressure and we can press it down together and we put it into a single location. Now I've drawn it off center just because there's other things interacting here. We could clean this up a little bit. I could put gravity acting on it here, MAG, and there we go. Now we're free to put the normal force on the bottom. Does it matter that I put gravity here on top? No, it doesn't. We could put it here passing through the center of mass. I could put it on bottom. The only thing that's really important here is that there's gravity acting on it. It acts through the center of mass, and we got the magnitude and the direction correct. Okay. What else? What else is acting on this thing? Well, it is sliding on this surface, right? And I could take my eraser and I can move my eraser around on this surface. Now, what keeps the eraser from just going off to infinity? Well, I applied a force to the eraser, I made it accelerate, I gave it energy, and then its energy dissipated. So there is some friction, right? There's friction associated with this surface, between the surface and the eraser. The same thing here, right? We've got some surface, we've got a block sliding on it, and there's going to be friction on this surface. We could simplify the problem down and call this some frictionless surface, right? Like ice or something slick. That's not generally true. So let's just put friction in here. So I'm going to call this one FC. So the C, I'm calling this like Coulomb. Coulomb friction is another word for sliding friction, so surface friction. Next, let's say that this block is actually representing, it could be a car, it could be a train, it could be anything moving, right? But something big, something moving through air, let's say. So we know that the air is going to have to move around this object, right? And when you do that, when you move through a fluid and you displace the fluid, there's going to be a little bit of drag on this from the fluid. So what we could do is we could put some other force on this, F sub D. I'm going to call this a drag force. Don't worry about the direction of these arrows just yet. Don't sweat that part. We'll talk, I'm probably going to make a little video just for friction, and we'll talk about how to deal with these terms right here. Ultimately, what you would want to do is you write it in this way. You just leave it symbolic for now. And we come back later, and we're going to eventually make some claim. We're going to say FC equals, we're going to put something in here, and we're going to say FD equals, and we're going to put something in here. And you might know where these parts are going. These are going to end up being functions of, this one's going to be a function of some coefficient of friction and the normal force. And this FD is going to be a function of usually speed and some geometric thing, like the cross section of the front of the block, something like that. We'll go back and we'll do these in their own videos. So for right now, just put FC and FD. That's okay. All right. What else are we missing on this diagram? What else could be going on? Well, if this was a car, right, then it would have some kind of engine, right? And that engine will be generating torque going to the wheels, and that would turn into a force pushing this thing forward. What else? We've got two different friction models. Let's do this. Let's put let's say that there is some external force. Excuse me. There's some external force here. I'm just going to call this F external. F external. Okay. So here is our free body diagram. Next, let's move on. Let's do some equations. You've got this part, right? You got this part in your notes. Let's write down the equations for it. So we said this was body A, right? So we're looking for sum of forces on body A. There's a free body diagram. You can literally just bring these things over. One thing to remember though, this equation, it's a vector equation, right? Each of these things, each of these forces, they're going to have some scalar component. They are going to be vectors though. So just keep that in your head. Make sure you get the directions correct. So let's, what do we got? Let's just bring them over here one by one. So we've got MAG. That's acting in the negative y head in direction. We have the normal force that's opposing it. Positive y head in. Then we've got a couple of, we got these friction forces, we got an external force, right? So plus FD acting in XN plus FC acting in XN. And then also we've got this external force, F external, and this is in the XN in direction. Okay, We can, if we want, we could take these and we could group them, right? We could arrange this by direction. Let's say FC plus FD plus F external, that's all on the X hat in, and then plus, we've got N minus MAG in the Y hat in direction. Okay, so sum of forces doesn't get much more complicated than this. If you can do your diagram, you can bring them over here and you can put them together. In this problem, it ends up being really easy because everything's in the in frame, right? Everything's in X hat in, everything's in Y hat in. The next example we're going to do is a pendulum, and we'll see in the pendulum example, it's a little more complicated, especially if we do like a double and triple pendulum. Then it's a big issue of what frame do you put your forces in, but we'll get to that in a bit. Okay, so hopefully everybody's okay with this. If you have questions, let me know later. Let's do the sum of moments on this one. Sum of moments on body A. Now, anytime you go to do moments, okay, something should go off in your head. We ran into the same thing when we were doing momentum, right? When we said angular momentum of this body, we always had to specify a point. Same thing here. If I say the sum of moments on body A, I also have to specify what the points are. So we want to take the moments on body A about point A. So in a very literal sense, how do you find the moments? Well, you probably know this, R cross F, right? Maybe from physics. This is a distance, right? This is a 3x1 position vector, R, and then it's being crossed against a force, and again, a force is a vector as well, so it's vector cross vector. So clearly a moment itself is a vector, right? In this problem with our syntax, this R right here, this is a position vector. Okay, so a position vector from something to something, from B to C, who cares, right? It's some position vector, and then you're going to cross it by a force. So we just need to do that for each one of these over here. So we just need to know the force, right, which we wrote them down already. And we just need these position vectors. So let's consider these forces acting in the vertical first. Where does gravity act? By definition, gravity is going to act at center of mass. If we're taking the moments about center of mass, we can write this down. I can say that this is the position vector from A to A. Cross, and then we can bring this over. We'll just say minus MAG Y hat in, right? We said PAA cross negative MAG Y hat in. That's the moment created by gravity. So first of all, how did we know that this was PA to A? Well, this R right here, the way that this R is set up, it's intended for you to apply some force at some point, okay, and then you're taking your moments about some other point. So this is the quick example I always use is a cantilever beam. If we put a force, external force moving up, we can see that the moment is positive, right? This force would make this beam want to bend in this direction. And that's a positive moment, so you can go through and you can say, okay, well, if this is A and this is B, in order for the result of this cross product to be positive, this position vector over here, it needs to be A to B. So the format here, when you're doing your moments, it's the position vector from the point that you're taking the moments about to the point where the force is applied. So up here, we're taking the moments about A, and the force is applied at B. We would do the position vector from A to B. So down here in this example, we're saying, okay, we want the moment created by gravity. It's PA to A. Obviously, PA to A is nothing, right? This gravity creates no moment, so this was the fun Little exercise just to prove the point. Yeah. Okay. Go. Go. Okay. So, gravity creates no moment. Same story with the normal force. The normal force, we're going to say it's going to act at the geometric center down here. If you wanted to, we could go through and we could say, okay, here's point A, and here's point B. And we want the moment created by the normal force. Okay. So here is P, A, B, cross, in the y hat n direction. We'll see what happens to this one in just a second. Next, let's finish this off. So we've got this Coulomb friction on bottom. Again, it's a question of where does this friction act, right? Because it's acting at the surface. Without having some other better information about it, let's just say that the friction force also acts here at this point B. So PA to B, cross, and we're going to say this is FC in the x hat n direction. Okay. Next, we've got this drag force. Let's say that the drag force is acting here. This is point C. So we've got plus PAC cross FD and FD in the x hat n. And then what do we have? We also have this external force up here. Let's call this one D. So finally, P, A to D, cross, F external, and this is acting in the x hat n direction. So I've gone ahead and took that sum of moments equation, I rewrote it up here. I did a little simplification, so I grouped these two terms together so we can just put them all in at once. And then we've got these other two over here. So let's go through and let's individually resolve all of these. And let's see what comes out of it. So position vector, A to B. We need to make sure we call all these out. A to B, A to C, and A to D. Tell you what, let's we'll just do them all one at a time with the moment. So A to B. Here's A to B, right? A is the center of mass, B is this point on bottom. So A is it's some distance, we can call it H, sure. It's H. It's H in the negative y hat n direction. And then we have here the forces. So what are we doing? We're going to say negative H yn cross, and I'm just going to bring these down. So it is cross in the y hat n plus fc in the xn, right? Here's the cross product. So what's going to happen with this cross product? Well, we've done this several times, right? We had to do a whole bunch of cross products with transport theorem. We know that we can distribute this. I can take this one and distribute it here. I can take this one and I can distribute it here. So we're looking at y cross y, which is going to be 0. And then we're doing y cross x. Y cross x is by itself negative z. There's a negative here in front. So we're looking at PAB cross ... this first term right here. So we're going to have the scalars h times f sub c. Y cross x is negative z. Negative in front makes it positive. So is this correct? Does this make sense? Well, just looking up here, there's the force. We can see that the force is moving this way, right, across that bottom surface, and that would make the block want to spin. So it's going to make the block want to spin just a little bit. Next, let's take care of this one, PAC. So PAC. Now it's just a question of how does the drag, right, this air act on the body. as I said, we're going to do a video later where we talk a bit more about friction forces and drag and things like that. For right now, though, you can maybe see how this is going, right? Like with the force acting purely in the x hat n, what happens if PA to C is just some distance d in the x hat n? Well, that means you would take this and you would put it here, right? And it would be x hat n cross x hat n. So if it is x hat n cross x hat n, yeah, come on. Okay. If it is x hat n cross x hat n, if we say d x hat n cross, and I'm just going to bring this down, fd x hat n, clearly we can see that this is 0. Clearly for me, maybe you have a cat in the way. All right, honey, go back to your chair. Let's purposefully not do that with this external force. We're saying that this, this force up here, this external force is acting at point D. With the external force, that means you're applying it in some way, or it's coming from an actuator or a motor, something like that. Let's purposefully put point D somewhere slightly different. So let's say PA to D, we're looking at, we're going to the left, so this is a minus D in the x hat n. And let's say that it's up a bit as well. So we could call this, let's say H2. H2 in the y hat n direction. Okay, so here's our position vector. We're going to put it up there. So let's say minus d xn plus h2 yn cross f external in the x hat n direction. Okay, we can resolve this. We know again that we can distribute these, right? You're going to end up with x hat n cross x hat n, 0. We're going to end up with this term right here. It's y cross x. And so here's the scalars, h2 times this external force, and then y cross x is, stop it, y cross x, quit it, go. Y cross x is negative z, right? Negative z, okay. So at the end of all of this, what did we do? We had our sliding block, we did our free body diagram, we did all the forces on the diagram itself, and then we come back and we write these claims. So let me finish now, and let me put all of this together. And let's say here was the sum of moments on body A. So back to the diagram, we said that gravity and the normal force, these aren't creating any moments. There was a little moment created by the Coulomb force, right? There was no moment created by the drag, and then there was moment created by F external. So what do we have? We had I'm going to call it H1. H1 FC, and then minus H2 F external, and these are acting in the Z hat n direction. So those are moments about Z. So this is an interesting final claim, right? We're saying that the sum of moments acting on this thing is equal to this. Now, is this block ever going to rotate? I mean, we came up with the problem definition, right? We said this is a block on a surface, and we said that a frame doesn't move. So we haven't gotten to equations of motion yet. We're gonna get to all that fun stuff, but just remember that the sum of moments is equal to the change in angular momentum, right? So if something is going on here, then something is going on over here, right? If the sum of moments is not 0, that means that the right-hand side is also not 0. So is the sum of moments in this case 0? Well, Fc is a Coulomb friction, right? That's sliding friction. So it's just some number, and H is some number, right? Like you multiply by height, you get a number out of this. H2 is a number, and then F external is specified. So are we guaranteed that these things are always going to cancel each other? Right? This is just going to be a function of N and coefficient of friction. These are constants. This one is specified. We could very easily pick an F external that does not cancel this, right? Like you could do that. If we could just say if this is 10, then make that thing 15. Boom, done. So what does this mean if this is our sum of moments? Right now with this definition, it tells us that this is not equal to 0. And if it's not equal to 0, then why isn't the block rotating, right? So we have to put something else in the model to make this block not rotate. You have two options. The first option, and the one that I do not recommend, here's your free body diagram. We said earlier that this normal force, it's actually representing pressure, right? We said that there's actually this distribution of pressure all along the bottom of this surface, okay? That's fine. Look at this F external. You're pushing on the top of it, right? You're pushing at the corner. And if you push at the corner, that's going to make the block want to rotate, right? We have that. It's right here. It's a negative moment. This block is going to want to rotate. And when it wants to rotate, this front right corner right here is going to drive down into the surface. Like it's going to push into whatever the surface is. And the pressure is going to actually build here at the front. So you're going to have a large pressure there at the front. And then this back corner right here is actually going to want to come up off of the ground, right? So this pressure here is going to be diminished. So what you're going to find is there's going to be a kind of a gradient of pressure all along this surface. Because again, the surface right here is keeping this thing from rotating. So the first thing you could do is you could let this normal force, let the normal force slide left and right. The magnitude of the normal force stays the same, but then it's acting at a different position. So that position is where the center of the pressure is. If you do that, then you're effectively adding a generalized coordinate. You're saying that force N, it doesn't act at the center anymore. Now it's acting at some distance Q that is sliding along the surface. And then you go through and you find, it would end up in this expression down here, and then you would say, okay, what distance Q cancels all of these forces, and then you solve for Q. So that's one approach. It's not the approach I recommend, actually. We could do something a little simpler. We can say, you know what, we're going to let N stay exactly where it is. We're not going to move it. And we're just going to combine it with a moment. So let's just call this one R sub M, a reaction moment. So the normal force is going to stay right in the middle. And whatever moment would have arisen from the normal force sliding, we're just going to model this as a reaction moment. So what that means is when I get all the way down here and I have my sum of moments equations, all I have to do is I take this reaction moment from the free body diagram and I add it, Zn, there you go. Now, what is the value of R sub M? Right now it's an unknown. I just kind of added it to the diagram. Well, the value of it changes. The value of it is whatever it takes to make these terms all here go to 0, right? Because we said if this thing doesn't rotate, then the sum of moments on it has to be equal to 0. There you go. Whatever is left over from these two not canceling, that is the instantaneous value of R sub M. Okay, so if you're working a problem, something real simple like this, what do I need you to do? I need you to start with your standard write-up. I need you to do a free body diagram. I need all of the terms, all the forces, any reaction moments, I need them here on the diagram. I want you to come off to the side. I want you to write expressions for the sum of forces equals, right, blah, blah, we did that. And then I want you to write expressions for sum of moments. If you need to start with some basic definition using cross products, feel free to do that. Put in the specifics of the problem, whatever these terms end up being. And again, a lot of these things you make up, H1, H2, right? You put those things in, you resolve the cross products, you give me the final term, okay? If you can do this, then you're going to be in a good position for the equations of motion.